So let's solve for the enthalpy of reaction from calorimetry data. Meaning, you did some kind of reaction in the lab, in a calorimeter. We're going to figure out what the delta H for the reaction is. So, starting with 2 grams of calcium, and I react this in 100 milliliters of 1 molar HCl. We observe the temperature to increase by 25.4 degrees. So first, let's write a balance equation. The reaction is happening. So calcium, would you consider calcium an active or an inactive metal? It's active. It's a second column. And active metals react with water to produce hydrogen gas and a metal hydroxide. So to balance this, we need 2 there, and yeah, it's balanced. Okay, so here's our balance equation. Calculate the heat change of solution. All right, so Q of what's in the calorimeter. Okay, so let's calculate our mass of our solution. Now remember, solution is when you add the sum of the reactants. So this is, I'm going to assume, it's not really an assumption, but 100 milliliters is 100 grams of water, right? Because the density of water is 1. Not to split hairs and go down to the fine hundredths and thousandths place, so density like we did in the first unit. But we're just going to call it 100 grams. So I'm talking about a mass of 102 grams for my solution. And we're going to use water-specific heat because it's primarily water. And the increase in temperature is 25.4 degrees. Okay, so (10,080 joules is what I get. Determine the heat change for the reaction. Okay, remember, so this is for the solution. The reaction, of course, is going to be the same magnitude but opposite sign. So negative 10,830 joules. Calculate the delta H for this reaction. The delta H for reactions by convention is in kilojoules per mole. So I just have to take this number and make some adjustments to it. Okay, so this is going to be divided by 1,000 to convert to kilojoules. So negative 10.83 kilojoules. And lastly, I need to figure out per mole what it is. How could I do that? Do I have any information that could lead me to moles? The mass, right? 2 grams. 2 grams calcium. Molar mass of calcium, 40.08. So 0.0499 moles of calcium. Okay. You might notice that in this reaction there are 2 reactants. Sure, calcium is one of the reactants, but what's the other reactant? Wait a minute. Sorry, I totally messed this up. This is not H2O. What am I doing? Not enough coffee today. This is HCl, right? It doesn't change our calculation. It just changed my equation. Sorry about that. We still get hydrogen gas. This is just calcium chloride, not calcium hydroxide. There we go. Okay. There's 2 reactants. HCl is my other reactant. So when you have 2 reactants, which moles do you divide your energy by? And the answer is the one that limits the yield. There's a name for that. What's it called? The limiting reactant. You got to divide it by the moles of the limiting reactant. Okay, so just to be sure, let's figure out how many moles of, let's figure out which one is the limiting reactant. So back up here, 100 milliliters of 1 molar HCl, so 0.1 liter times 1 molar is 0.1 moles of HCl. All right, so 0.1 mole of HCl We got to pick a product to be our yield. We'll just pick, doesn't matter, calcium chloride, I guess. So our ratio is 1 calcium chloride for every 1 calcium. And then for HCl, requires 2 HCl's for every calcium chloride, so it ends up being 0.05, which, look at these numbers, guys. Aren't these effectively the same? So I think ideally this is most likely intended to be the perfect ratio, right? So in other words, if the numbers are the same, if your yields are the same, that means they're both limiting reactants, so it means it doesn't matter, okay? But we're going to use well, I guess technically it is lower. We'll use calcium, I guess. So divided 0.0499. Normally it's not this close. All right, negative 217 kilojoules per mole. Okay, so how we went through this reaction was essentially almost the same way you do heat of solution, right? You needed Q because you needed to find the amount of energy absorbed by the calorimeter contents. You know that the Q for the calorimeter is equal but opposites to the Q of the reaction, and then you just divide by the moles. There you have it. Okay. So now let's just revisit mole ratios and how they apply to thermochemistry. It's really nothing different. This is kind of straight up stoichiometry, but you still need to see examples of this being done with delta H values. All right, so according to this first equation, when hydrogen and chlorine react, we form 2 moles of HCl. And the delta H for the reaction is negative 185 kilojoules. Okay? So 185 kilojoules is evolved when 2 moles of HCl are formed. So what you should note is this type of reaction here has a name, and I went over it yesterday. If you had to give that kind of reaction a name, what would you call it? Synthesis. Oh yeah, it's a synthesis, that's true. Heat of formation, enthalpy of formation, heat of formation, right? And so if I said, all right, well, what's the delta HF for this reaction? Delta HF values are on a per mole basis. So what do we have? Negative 185 kilojoules. How many moles of the compound are being formed? According to the reaction. So really, the delta HF for this reaction will be negative 185 divided by 2. Okay, and this is something to be careful. This is a common oversight. If people see a reaction and they said, all right, well, what's a heat of formation? It's got to be per mole. So in this case, you have to divide by 2 because the reaction is showing you 2 moles being formed. Okay, another example. Mercury oxide is shown here to decompose. Here's the delta H for this. 182 kilojoules of heat must be absorbed to decompose 2 moles of mercury oxide to its elements. Now, so it says endothermic, the sign is positive, right? So think about that. We're breaking apart a compound, it's releasing energy, okay. Use a stoichiometric approach to solve for the delta H that occurs. Okay, so what is the enthalpy change if we form 50 grams of HCl? What is the enthalpy change? In other words, they're asking for how much heat, how much energy, right? How many joules? So, 50 grams of HCl. Grams will not help you here because all of your terms here are involve moles. So the molar mass of HCl, 36.46. Okay, so we got 1.372 moles of HCl, and we're forming the HCl, so we should use -92. You know what? Scratch that. I'm going to write it how you'll probably see it. There's going to be negative 185 kilojoules for every 2 moles of HCl. Because someone who's given a problem like this, the first thing that they're going to see is this. They're probably not going to do this step, which if it's not asked, they're not going to do this. They're just going to see this. So this is how we set up. But we're still doing it. We're still dividing by 2, so it's the same thing either way. All right, so times 185 divided by 2. So there will be a release of 127 kilojoules. Which makes sense, right? Because the amount in the equation is per 2 moles. You know, we had more than 1 mole, so it's going to be more than 92. All right. So the point of this is to show you, to get you used to writing this value from here, writing this value and using it stoichiometrically. Okay. All right. So then, laws of thermochemistry. The change in enthalpy is directly proportional to the amount of reactants or products. So what releases more heat? A gram of gasoline or a gallon of gasoline? Gallon. Okay, it's proportional, right? So using the delta H from above, what's the change in enthalpy for 1 gram of chlorine? So 1 gram of chlorine. Okay, so chlorine, the molar mass of chlorine diethylmethylchlorine is 70.9 grams. And in that equation up here, for every, there's going to be negative 185 kilojoules for every 1 mole of Cl2 that reacts. So there'll be a release of negative 2.6 kilojoules. That's assuming that's the limiting reactant. Okay, so are you guys okay with the proportionality of heats of reaction? It just means you can use it stoichiometrically. It means it's proportional. That's all it means. All right. Law number 2. The delta H for a reaction is equal in magnitude but opposite in sign if the products and reactants are reversed. Meaning, if you have any reaction that has a delta H value, like a thermochemical equation like this, right? This right here has a thermochemical, it's a thermochemical equation because the delta H is provided, the enthalpy is provided. If I wrote this backwards, right? If I said 2HCl goes to form H2 plus Cl2, the delta H would then be the opposite of what was originally listed at. It would be positive 185. That's all it's saying. You flip the direction of the reaction, you just flip the sign because you're doing the opposite thing. Okay. Another example. This reaction right here, H2O solid forming H2O liquid. Well, isn't that melting? Right? It's fusion, right? So if you melt something, the sign is positive because energy is required. So what if we wrote that backwards? And we said, all right, well, liquid water is forming solid. Well, isn't that freezing? Which is the opposite process, which is why energy is released. Freezing is an exothermic process. It's kind of weird to think about, right? But when you're from this perspective of the system, or the perspective of the reactants and products, energy is going to be released if it's freezing because it's all of its molecules, its molecular motion is slowing down, right? Whereas melting is endothermic. That one's easier to picture, right? You know it takes energy to melt something. Okay. All right. Law 3. We can combine equations to find an overall delta H. So if you're able to algebraically combine two equations, then the delta H for the reaction is the algebraic sum of the previous two delta H's. But it's only if they algebraically combine. You can't just combine anything. There's got to be some reason, some bridge for them. That means there's some kind of common reactants or products. Okay, so this third law is what's known as Hess's Law. Hess's Law. So if you don't know the delta H for a reaction directly, we can find the delta H for the reaction by combining two other reactions that lead to it. So for example, I don't know the delta H for this reaction. For the carbon that reacts with oxygen to form carbon monoxide, I don't know the delta H. But two other reactions are known, and their delta H values are known. So I can manipulate these two to eventually get the unknown value. So it's just some really simple rules. All you have to do is take a look at the given equations, and you have to make sure that your reactants and products are on the correct sides. And then if things cancel out and add up, then you're done. Okay, so from left to right. My first reactant in this unknown equation is carbon solid. Where is carbon solid in my reactants or in my equations that are given? It's right here. Okay, so what that tells me is that this equation is written in the correct direction. So I'm just going to rewrite it. Okay, all I did was rewrite that. Now, the oxygen. So oxygen is right here in the secondary reaction. But also notice that the CO2 right here, notice that CO2 is not in the overall equation at all. If CO2 is not in the overall equation, what that means is CO2 is something that is algebraically canceled. Now, when we wrote this equation here, we verified the direction of this equation. And this equation shows CO2 as a product. But if CO2 cannot be in the overall reaction, that means we have to write this equation in such a way where CO2 cancels. Which means we need to flip that first equation given. So I'm going to rewrite it as CO2 forms CO plus 1/2 in O2. And because I flipped it, I'm taking the opposite of what was written for its delta H. Okay, now let's see what cancels. CO2 on the reactant side and CO2 on the product side cancel each other out. What else cancels? Half NO2 is subtracted from both sides. So the result is carbon plus half NO2 forms carbon monoxide. We have algebraically formed the third equation, the equation they're asking for. And once we see that this works, now we can simply take the sum of the individual delta H's and add them up. All right, so negative 393.5 minus a negative 283. And that's how we do Hess's Law. This is entirely possible because enthalpy, it doesn't matter how you got here, right? It just matters what the state is. Enthalpy is a state property. Okay? Doesn't matter which way you calculated delta H, it's going to be the same. All right, let's try another one. Let's find the delta H for the process of converting graphite into a diamond. Here's what we are given. Graphite plus O2 to form CO2, negative 394. Diamond plus O2 to form CO2, negative 396. In the equation that is desired right here, there is no O2 or CO2. That means both of those must cancel. So I need to combine these two, but before I combine them, I might need to manipulate one or both. What should I do in this case? Which equation should I alter? The second one, yeah. So let's rewrite this as CO2 forms carbon and diamond form plus O2. So when I combine these two together, the CO2 cancels, the O2 cancels, and what you're end up with is C graphite forms C diamond. Now when I flipped it, this is the opposite of negative 396, or in other words, it's positive 396. So delta H is equal to 2. You guys getting the hang of this? Right? In a situation like this, you will be provided with the equations, but you have to manipulate them correctly to find what the delta H is. Okay, this one's a little bit bigger. So what we're trying to find is this reaction's delta H right here. I'll give you a second here. You guys see if you can manipulate through. All right, let's start talking about this. So I recommend finding the biggest things first, the biggest formulas first. So when we look at this, the biggest thing I see here is that, uh-oh. Can I stop sharing that? All right, that was weird. So the biggest thing I see here is this formula B2H6. Okay, so B2H6 has to be on the product side, and here it is on the reactant side. So right away I know that this second reaction has to be flipped. I know the first reaction is written in the correct direction because boron solid is a reactant. So let me just start with that. I'm just going to rewrite everything on the right-hand side. So 2B plus 3 halves O2 forms B2O3. And I'm flipping the second reaction. So B2O3 plus 3 water. And I'm going to include the states here because water is in a couple of different states and we need to be specific. I'm not going to write the states for the other ones because the other ones, they're not specific. Okay. All right. So as it stands right now, does everyone see how B2O3 would cancel? Okay. So the thing is, in our overall equation here, do you see any water? No. So the water must also cancel. So let's continue on. Now, this water here is in gaseous form, right? So I need to find where water is a gas form, which is on the bottom. And if there's 3 moles of water gas on the reactant side, then I must have 3 moles of gas on the product side. So that means this reaction at the very bottom, I'm going to multiply it by 3. Okay. You know, actually, I need to get caught up here with my enthalpies. I'm gonna write these down real quick. So negative 1273. This one was flipped, so that's the opposite of negative 235. And multiplying this one here by 3. Okay, and so now we need to, do we need the third equation? What do we need to do with the third equation? Do I need to include it or can I leave it out? Yes, I have to include it, yeah. Because it's liquid water, right? See this liquid water here? Right? There's no liquid water on the reactant side, so this liquid water must be canceled. So that means I need liquid water to be on the product side, which it is, but not in the correct proportions. So that means this has to be multiplied by 3 as well. So we're going to have 3H2 plus 3 halves O2 to form 3 water in liquid form. And so the delta H will be 3 times negative 286. All right, let's see what shakes out. Okay, B2O3, we said that's the first thing it's canceling. There's one on the product side, there's one on the reactant side. That's gone. Water in gas form, 3 moles of water gas on the reactant side, 3 moles of water gas on the product side. Gone. Water in liquid form, 3 moles of liquid water on the reactant side, 3 moles of liquid water on the product side. Okay, our final equation has no oxygen in it. But here we have 3 moles of oxygen on the product side. And we also have 3 halves plus 3 halves. Well, what's 3 halves plus 3 halves? 3. So the oxygens all cancel, and the only thing we have left is this, this, and this. So we rewrite our final equation. And that works out. And if it works out, then I can now take the sum of my values. Did you guys get 36? All right. Another example of Hess's law. Now, this one had 4 equations, okay? You know, you'll be working with anywhere between 2, 3, 4. I don't think you'll see anything greater than 4. You probably won't even see 4 all that often. But this is how you do it. This is Hess's law. Additivity of heats. Individual reactions can be added to produce a new delta H for a third reaction. Okay. This we actually went over this yesterday. Remember, with heat of formation. It's here, so let's revisit. Delta H of F is the heat of formation when 1 mole of a compound is formed from its elements in their natural states, right? So they have to be in their natural states, meaning you have to know whether something is a solid, liquid, or gas, and this is happening at 25 degrees and 1 atmosphere pressure. Okay. So this is a heat of formation reaction. Notice that there's negative 254 kilojoules for every 2 moles. That's why on your chart it is listed as negative 127 because it's on a per mole basis. So this was divided by 2. Okay. This reaction here, it shows decomposition, but if we wrote this backwards, we would flip the sign, and this is a heat of formation reaction. So the delta H would be the opposite of what was provided. And that's why when you look up this value, this is how it's listed on your chart. In order to do the ASA, we had gone over how you take the sum of the heats of formations of products minus the sum of heats of formations for reactants. And so we did enough practice with that, I think. Okay. And I think we're going to stop here for today.